All right, Poisson distribution, homework. This is section 5.4. Um, First of all, the Poisson distribution, you're given a formula in the PowerPoint and even in the videos that I showed in class. Thing is, you don't need the formula. The calculator will do all the work for you. It only requires two entries. All right, but there is a little twist. We're going to be using Poisson PDF for an exact value, 4 successes, 5 successes. And sometimes you'll be asked for a range of successes. Then we'll use a Poisson CDF, very similar to what we did with binomial PDF and binomial CDF. If you're asked for the front end, you can just use the CDF and tell the calculator to stop when you want to stop adding. It'll always start adding probabilities at zero. If you're asked for the back end, well, then you're going to have to find the front end and subtract the answer from one using CDF. The only little hiccup here is sometimes you have to be aware of the time change. All right. Sometimes they'll give us the mu for a particular time interval, but he'll ask a question for a different time interval. If the different time interval decreases, your mu, your lambda value is going to decrease. If your time interval increases, well, then your mu is also going to increase. And we'll talk about that as we get to those problems. I think they're obviously towards the end, numbers 7, 8, and 9, whatever. Anyways, where do you find, this Poisson PDF? That's how we start off. You hit second function bars, you go down to letter C, and there it is right here. There is your Poisson's PDF, and then if you're looking for a range of successes, you'll be using Poisson CDF. All right, for the first problem, he flat out gives me what mu is. Now, mu and the calculator uses this Greek letter lambda. Some textbooks use lambda for the mean. All right, lambda and mu are synonymous. All right, so in this case here, mu is given to me as 7. We're looking for the probability of exactly 6 successes. All right, there's my x value. Put that in, and the calculator very nicely returns an answer of 0.14900. Now, here again, I'll stress this again. Before I even started the problem, I would have looked at all my answers. I would have seen that all my answers have 5 decimal places. I would have gone to my mode, come down to my float, set my float to 5 decimal places. I want this answer to be right on, right here, all right? Most of these will be spot on, maybe a minor discrepancy. All right, Poisson distribution. Number 2, random variable x has a Poisson distribution. The mean is 0.733. Find the probability that x is equal to 2. All right. I go to second function bars. Come down to letter C, Poisson PDF. I'm looking for exactly x, exactly 2. Put in my mean, 0.733, as I was given. My x is 2. What could be easier? You can see where I don't need any formula at all. My calculator returns 0.12907. Here it is, letter A. All right, so we have a word problem. A naturalist leads whale watching trips every morning in March. The number of whales seen has a Poisson distribution with a mean of 2.3. Find the probability on a randomly selected trip. Notice the time change, right? He's given the mean per trip. He wants to know something about a particular trip. All right, the time interval has not changed. Find the probability on a selected trip. The number of whales seen is equal to 4. All right, so there's my mean, 2.3 as he gives me. And he wants X, he wants to know the probability of seeing exactly 4 whales. X is 4. Poisson PDF, exactly. There's my lambda, my mu, one and the same. My X value is 4. Straightforward, 0.1169. All right, let us see. Number 4, a lightning strike. My cell phone is ringing. I'm going to let it ring. Number of lightning strikes in a year at the top of a particular mountain has a Poisson distribution with a mean of 4.2. I wish this phone would stop ringing. There it is. Not quite. Once again, the number of lightning strikes in a year at the top of a particular mountain has a Poisson distribution with a mean of 4.2. Find a probability that in a randomly selected year, the number of lightning strikes is exactly 0. All right, so Notice my time change has my time limit, my time interval hasn't changed. He gives me the mean per year. He wants to know something about a year, a selected year. All right. So my mu is 4.2, and we want to know probability of getting 0 lightning strikes. My x value is 0. Poisson PDF, straightforward. There's my mu, my lambda, 4.2. X value is 0. And my calculator returns 0.0150. Once again, 4 places. I would have looked at this prior to doing the problem, and I would have set my float to 4 places. A mountain search and rescue team receives a mean of 0.56 calls per day. Find a probability on a randomly selected day they will receive fewer than 2 calls. Notice the time interval here again. Now my home line is ringing. The same person that was calling me on my cell is trying to reach me on my home line, but I'll get back to that person. Anyways, 0.56 calls per day. Find a probability on a randomly selected day. Time interval hasn't changed. They will receive fewer than 2 calls. Okay, so fewer than 2 calls. X is less as an inequality. X is less than 2. Fewer than 2 translates to X less than 2. So looking for a range here, all right? We want the probability of 0 and 1. Yeah, could I use PDF twice and take these two answers and add them? Yeah, I could. But a faster way is to use a Poisson CDF. It'll start adding the probability at 0, and it'll stop adding when I tell it to stop adding after it adds the probability of 1. All right, so mu is 0.56. That hasn't changed. The time interval hasn't changed. It's per day. And I'm going to tell the calculator to stop adding at 1 after it gets the probability of 1. It'll automatically start at 0. So there it is, Poisson CDF. My mu, my lambda, is given to me as 0.56. I want it to stop adding after it gets to 1. All right, 0.8911, and letter B. In a town, the number of burglaries in a week has a Poisson distribution with a mean of 4.6. Find a probability that in a randomly selected week, notice the time interval has not changed. He gives me the mu in regards to a week. He wants to know something about a week. What about this something? He wants to know probability of at least 3. Well, as an inequality, at least 3 means x is greater than or equal to 3. At least 3 means 3, 4, 5, 6, and so forth. All right. So what I'm doing here, I'm trying to solve for this back end, which I couldn't do because this would go on to infinity. What I am going to do is use CDF. All right, tell the calculator to stop adding at 2. Calculator will find this answer, and I'll tell it to take this answer and subtract it from 1. So when I enter in the CDF, I put in 1 first, minus, and then I go to Poisson CDF and tell it to stop adding at 2. So there's my mean. I want it to stop adding after it adds the probability of 2. All right, but what you're not seeing here is I started out by putting 1 first, minus this answer here. All right. So 1 minus this answer here gives me 0.8374, which is the probability of 3, 4, 5, all the way out to infinity. The back end hasn't changed. We haven't seen it for a while, but we did it when we were doing binomial CDFs, back end, subtracting from 1. Town of Fastville has been experiencing a mean of 63.6 car accidents per year. But now notice, he says here, find a probability on a given day. Well, the time interval has changed. We're going from a year. He wants to know something about a given day. Now, we realize there are 365 days in a year. What does he want to know? He wants to know the probability of exactly 3 accidents in Fastville. So X is equal to 3. Now I'm taking the mean of a year. Number of accidents in a year, 63.6. He wants to know something about a given day. So I took the mean per year and divided it by 365. I now have the mean number of accidents per day, 0.1742. Entering in, here again, I'm using PDF because I want X is equal to 3. Exactly 3, PDF. There's my new mean per day. There's my X value. excuse me, my calculator returns scientific notation, but e to the negative. Negative means move the decimal point to the left, in this case, 4 places, which puts 3 zeros prior to the 7. Now notice you're off. It's just a smidgen. This is nothing else even close. But here again, I will, remind you, I'll emphasize, before I started this problem, I realized that all the answers had 6 decimal places. If you had your calculator set to 3 places or 2 places, you wouldn't even get anything close. Look at the number of places prior to doing the problem. You want this answer here to be as close as you can, all right? If you had 1 or 2 places, I don't know, the answer would have been 0. You wouldn't have seen 0, so I can't stress that enough. Number of calls received by a towing service is 19.2 per day. And a day has, 24 hours? We know that. He says, after finding the mean calls per hour. So what I'm going to do is, since this is per day, I want to take this mean per day divided by 24, and I'll have the mean per hour. You got to be cognizant of that. Sometimes the time interval changes. What is he asking me? After finding the mean, he says, find a probability that the selected hour, the number of calls is exactly 2. There's 2 calls. X is 2. I'm taking the mean number of calls per day. Since there's 24 hours in a day, 0.8 is the mean per hour. All right, dividing the mean per day by 24, I have now the mean per hour, 0.8. All right, so there's my mean, my lambda, 0.8. I'm looking for exactly 2. PDF, 0.1.14379. Letter C. On a tropical island, hurricanes occur with a mean of 2.41 hurricanes per year. Assuming the number of hurricanes can be modeled by Poisson distribution, find a probability that during the next 2 years. Well, it gives me the mean per year. He wants to know something about what's going to happen over the next 2 years. I'm going to take the mean per year and double it. I'll now have the mean for 2 years. What does he want to know? He wants to know the number of hurricanes will be exactly 3. X equals 3. Taking the mean per year and doubling it, I now have the new mean for 2 years. All right, Poisson PDF, there's my mean, my mu, lambda is a calculator. Mu and lambda are one and the same. I want my X to be exactly 3.1506. Sunita's job is to provide technical support to computer users. Suppose the arrival of calls can be modeled by a Poisson distribution with a mean of 5.2 calls per hour. What's the probability in the next 5 minutes? Now, what part of an hour is 5 minutes? And they want to know in the next 5 minutes there will be 2 or more calls. Well, 2 or more is X is greater than or equal to 2. 2, 3, 4, so on and so forth. All right, so I'm finding what's called the back end here. Well, I can't do this manually because this goes on to infinity. I'm going to use Poisson CDF, take this answer once I find it, and have a calculator take this answer and subtract it from 1. But I'm putting in the 1 minus before I even do all this. All right, so I'm taking the mean per hour, and since 5 minutes is 5/60th or 1/12th of an hour, the mean per hour is the mean. The mean for 5 minutes is the mean per hour multiplied by 1/12. Since 5 minutes is 1/12th, the mean has decreased by by 1/12th. It's 1/12th of the original because 5 minutes is 1/12th. You got to be aware sometimes the time interval changes. I take the mean per hour multiplied by 1/12 since 5 minutes is 1/12th of an hour. Bottom line is, notice what I did here. I made sure that I had 4 places. Reason being is I looked at my answers prior to doing this. I saw all 4. I want to make sure that this is at least a 4 places, just like the answers. I don't want to, have this just be 0.4 or even 0.43. All right. For preciseness, I used the same number of places that were in the answers. All right, so it's CDF. I'm going to tell the calculator 1 minus. I'm going to have the calculator use Poisson CDF and stop after it as the probability of 1. It always starts at 0 and stops when I tell it to stop. What I'm doing, I'm finding this answer and I'm taking this and subtracting it from 1, the back end. 1 minus this, all right? Whenever you're doing the back end, you're always going to have to subtract from 1.0707. All right, as far as the email that I sent out, um, didn't realize, and David helped me and reminded me that the last day of instruction is the 29th of Monday. All right, the 30th is reserved for what they call a reading day. Reading day simply means that instructors, if they want to, can have a review session, which I was going to do anyways. But the idea is it's not mandatory. I won't take attendance. It's not mandatory that you show up. If you do have some questions and you're available, I'll be in class at 12:30. I will work individually with folks, and we can go over anything from the Poisson distribution or anything else from section 7123, and I'll work with you. Feel free, however, if you can't make it on that Tuesday, you have um, other priorities, you can just shoot me an email and I can actually create a YouTube video for a specific section and question. Be precise. I need help on number 7 on section 7 too. I feel free to do that. Um, after I record this, actually going to email it to everyone to make sure. And also, I'll post this video on Blackboard. Um, Sorry for any confusion this has caused, but Tuesday will not be a mandatory class if you're available. Now, I've heard that there's a situation where the room, the gym, or some of the rooms may be closed since instruction. I don't know. Put it this way, I'll be there probably about 12:15. Yeah, I doubt very much they're going to close the gym up, but we'll see if our room is locked. But I'll deal with that as the case as it comes up. I'll be there about 12:15. If you can make it, fine. If you can't, just make sure you go through, you download all of the PDFs. If you have any questions between now and Thursday, feel free to email me. I will answer them for you. All right, hope this helps.